really windy, and we were all walking super close to each other, so I knocked Susanna in the head, and I gave her a nod.
That wasn't nice.
It was an accident with my phone.
Okay, so for those of you that are joining us via video, what we are studying today is the beginning of our next unit on data analysis, and we're looking at the counting principle. But before we delve into that, we're going to look at a way to illustrate how many outcomes there are using a tree diagram. So this is a tree diagram which shows how the school cafeteria can sell sandwiches if you get to choose from one of each of the following categories. So you have two choices for bread, white and wheat. Now, on the one that I ran off for you, these branches are separate. Do you see that? Okay. And then you have two meats to choose from, turkey and ham. And then you have two condiments to choose from. And on your sheet that I've run off for you, it says ketchup and mustard. But I thought that sounded gross. So I changed it to mayo and mustard. That's because we're in the South and we don't put ketchup on regular sandwiches. All right. So if we were to create a tree diagram, this is what it would look like. Does that make sense, guys? So we start off with our main deli, which in this case is a sandwich. And then we have two choices for breads. We have two choices for meats. And we have two choices for our condiments. Now, if we look at the ending branch, that shows us how many possible outcomes we have. So if we look at this, we have 1, 2, 3, 4, 5, 6, 7, 8 different possible outcomes. There are 8 different sandwiches we could create given these parameters. Does that make sense?
Yes.
All right. So we have 8. That's not an 8. All right, so now let's look at this example. Create a tree diagram to show the possibilities. When getting breakfast in the morning, you can choose from pancakes, waffles, or eggs as your main entree, with orange juice or apple juice to drink, and with sausage, bacon, or ham as a side. So we're having, okay, so yours says scrapple, and I changed that because we don't eat scrapple in the South. But let's Google this real quickly. It looks like a breakfast meatloaf.
Oh, that's yum. It sounds like breakfast meatloaf.
Scrapple.
Did you just say breakfast scrapple?
Okay, so here are, if you're looking at yours,
Scrapple. It's like spam.
it is, I guess it's similar to spam maybe? I'm not certain. Okay, so apparently that is scrapple. And now you see why I changed it to ham, because that's what we do. All right, so we can choose from for our main entree. So let's do main entree. We've got pancakes, waffles, or eggs. And then we have a drink choice. So our drink choice is orange juice or apple juice. Orange juice or apple juice. Orange juice or apple juice. Okay, and then we decide sausage, bacon, or ham. Sausage, bacon, ham. Totally going to run out of room here.
Yeah, that's what I
Sausage, bacon, ham. Sausage, bacon, ham. Sausage, bacon, ham. Sausage, bacon, ham. Sausage, bacon, and it should be a lot prettier, but we don't have much room here. And I think you have even less room.
Yes.
Yeah.
I fit it.
All right, so if we count the ends of our branch, 1, 2, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18 possible breakfast choices.
Didn't you just go to the second to last thing and multiply that by?
Yes.
Oh, yeah.
Yeah, you just count. Can't you just multiply the number of each?
That's what we're
Yeah,
about
orange
to
juice and apple
do.
juice.
You sure can. A tree diagram is nice because if you had 18 possible outcomes and and they just made different plates, and you just randomly went up and got one, what would be the probability that you would get a selection that had waffles and bacon?
180. Oh, wait.
Well, let's look. How many waffles have bacon? 1, 2, out of how many possible?
190.
18. So it'd be 1/9. So a tree diagram is nice for things like that. All right. Now, this is what yours look like. So it was similar, yet different. Okay, the next part is on counting principle, and that's what Bethany just wanted to use. So if there are m ways of making one choice and n ways of making a second choice, then there are m times n ways of making the first choice followed by the second. This is generally used when the tree diagram is too large to construct, or you just don't feel like making one. So let's get back and look at this. How could we have done it here? So we could have done it here for our sandwiches. We had 1, 2, 3 different categories. So if we look at our different categories, we had a bread category, we had a meat category, and we had a condiment category. So how many breads are there? 2. How many meats are there? 2. How many condiments are there? 2. And so if we multiply those choices for each category, we get that there are 8 possible outcomes. Isn't that what we got with the tree diagram? All right, let's look at our breakfast here. Do the same thing. Main entree. How many main entrees were there? 3. Drinks. How many drinks were there? 2. And how many sides could we choose from? 3. What is 2? 3 times 2 times 3 is 18. So isn't counting principle nice? Yes. All right, so now let's actually do some different application of them. So here are our examples. We're choosing a computer password, and the password is 3 letters followed by 3 digits. So we were given this information, and we have to stick to it. How many passwords are possible if the letters must be uppercase? Well, how many uppercase letter choices do we have? 26. So for our first letter, we have 26 choices. It didn't say anything about we can't repeat, does it? So for our second letter, we still have 26 choices. And for our third letter, we have 26 choices. Now we're on to our digits. How many digits are there? 9. 0 to... Wait. No. 10. 0 to 9 is 10 digits. So for our first digit, we have 10 choices, 10 choices, 10 choices. So how many possible outcomes are there here? 17 million. Good. 576,000 possible passwords given these parameters. Okay? 17,576,000. That is a big number.
That's why I can never remember my password.
Plus, you can have lowercase.
I struggle with those sites that make you change your password like every 3 months.
What sites do that?
Some of the teacher sites I log into, and so I basically have to keep a book, and in my book I have to write down my newest password. And one of my passwords along the way was "I really hate this site." Was my password. This is stupid in all caps. Yeah.
My parents, we have like a door lock, like our lock is a keypad, and then we have a garage door that's got a keypad, and the alarm has a keypad, and they're all different passwords, and they change them every 2 months. And do you know how many times I've called the police, like
You've set the alarm off?
Setting the alarm off, because it's 3 passwords that change every 2 months, and I never remember them. It's ridiculous.
I change most of my passwords.
And my parents won't let me write them down. They're like, don't write them down. What if someone finds them? Then they'll break into our house and like, see you. I just have to remember it.
So it doesn't really matter.
Wow. That's impressive.
It's like, can I keep it on my phone? I never know how my phone. They're like, no, if someone gets your phone, they'll break into our house. Like, they won't know what the numbers are.
Maybe you could put like Granny's birthday.
No, my parents say
that would be your secret place to store your password.
my parents
you could
say
call it
birthdays are
Granny's
too
birthday.
obvious, so they won't let us send me birthdays this word.
Wow.
Nor my neighbors.
That's serious.
Too obvious too.
All right. Let's take a look at the same situation, except this time No letter or digit can be repeated. So, for our first letter, we still have 26 choices, but for our second letter, we are now down to 25. And our third letter, we are down to 24. Now we start with our digits. For our first digit, we have 10 choices, but then we have 9 and then 8. So we have 11 million now. 232,000 passwords available.
You're never going to crack this person's phone. You're never going to crack this password.
You'd think not, but a lot of people tend to use some of the same stuff. And you can use programs.
Because there's only so many birthdays you can do, and lots of people do their birthday. There's a lot of the same passwords.
I do my passcode off of cool patterns.
Oh, all passwords are the same thing. That way I never forget it.
Yeah.
Yeah.
All right.
The same thing.
All right. So now we have a company that has extensions. You know how if you call up and it says if you know your party's extension, please press that now. Well, a lot of companies have extensions that will on the phone that will take you to who you want to talk to by avoiding the operator. So this company has a 4-digit extension, so that's pretty large. How many extensions are possible if there are no restrictions? So if we have a 4-digit extension and there are no restrictions, how many digits are there available? 10, 10, 10, 10. Or which we could have written as 10 to the 4th, right? So there's 10,000 possible extensions for that one phone number. Okay? Now, this part 2. How many extensions are there if the first digit cannot be a 0 or a 9?
8.
Okay, so that gives 8 for the first digit. Do we have any other? Nope, we didn't. 10, 10, 10. So that would just be 8,000 extensions. Now, in our third example here, how many extensions are possible if the first digit can only be a 1? So it'd be 1,000. We only have one choice for our first digit, but we still have 10 for the other 3. So that's 1,000 possible extensions. Any questions? All right. So today we have practice. Some of the problems I have on your practice might be slightly more challenging. Some of them are not. And then you also have a review of probability at the end of your homework. So your homework is a worksheet. If you're watching this video because you missed class today, your note sheet and your homework will be posted to the website so you can join up with us tomorrow.
Oh, did I